My name is Tony Shaska. I will talk about weighted greatest common divisors and weighted heights. This is it's a work that is a joint work with Beshaj and Gutierrez, and we'll just briefly describe what goes on in this paper. So let's just consider the following problem. I want to do some arithmetic in the moduli space of genus G curves. Okay, so this is an algebraic variety of dimension 3g minus 3, and therefore it can be embedded into a projective space. So what do we want to do there? Well, let's just remind ourselves that if x is a curve defined, let's say, over the rationals, then the corresponding moduli point is also a point defined over the rationals. The converse is not true. If the moduli point is defined over the rationals, there is not necessarily a model of the curve defined over the rationals. In other words, the moduli space is not a fine moduli space. It's a coarse moduli space. Also, one thing we want to consider is that if I do have rational moduli point, and let's say f is the minimal field of definition, so remember, not necessarily the rationals, then we know that there is actually a field extension, a finite field extension, so a number field over the rationals, and the degree of that extension is called the abstraction. Okay, the degree of that extension field. So what do we want to do? Here are a couple of questions that I have been considering in the last few years. So can we somehow count the rational points in the moduli space? Moreover, if we can count, then can we somehow split or at least decide how many of them have non-trivial abstraction or trivial abstraction? So the first naive way to do this is to actually say, okay, let's just embed the moduli space now in the projective space, and let's just look at it, and we have a way to count points in the projective space, namely the height machine through this a la veil, through the veil heights. And so we want to do that. One very nice and important property of the heights in the projective space is the following. Given a bound for the heights and given the bound for the number field you are working over, there are finitely many projective points of bounded height. So what does that mean in our case? It means that if I take a point, take the moduli space, embed it into a projective space, and call the corresponding point, the height of the corresponding point the moduli height, that means that there are finitely many curves, up to isomorphism classes of curves, with bounded moduli heights. And so this was our initial point, and I wanted to do some computations on this and see what I could say much about genus 2 first, and then you'll see that this is not enough, and then we have to look at these things not exactly on the projective spaces, but in these weighted projective spaces, and there was no height there. And we had to basically consider the option of maybe defining a height there and try to develop the theory of the height machine for these weighted moduli spaces. I will show you why we have to do that. So let's just consider a genus 2 curve. So a genus 2K, so the moduli space of genus 2. Well, a genus 2 curve, it looks something like this, right? And so two genus 2 curves are isomorphic if and only if they have the same absolute invariance, and these are the absolute invariants. And they are given in terms of the Igusa arithmetic invariants. In the literature, they are always denoted by J2, J4, J6, and J10, where the subscript actually denotes the degree. So these are homogeneous polynomials in terms of the coefficients of the the curve, and the subscript is the degree of such polynomials. So you notice that these absolute invariants, they have the same degree, numerator and denominators, and that's what it makes them GL2K invariants. And these J2 through J10 are SL2K invariants, but not necessarily invariant, just SL2 invariants. Okay, so a point in the affine moduli space now will be a point of this absolute invariance. Now, if you want to consider this as a projective point, you have to basically multiply this point by this constant J2 to the fifth, and that makes that point a projective point, which looks like this. So here is what we want to actually compute the heights of such points. And that's fine, but there is one problem here that you notice that each of these coordinates have very high exponents. And so that means that you are dealing with very, very large numbers, and the heights are relatively high, I mean very high. So intuitively, I mean naturally, you would say, why do I need to really keep track of these tuples when really what's important here are these tuples J2, J4, J6, and J10, right? After all, they do have all the information, but they do not uniquely determine the isomorphism class of the curve. So in order for us to actually understand how to do this, we have to understand up to what point these invariants determine the isomorphism class of the curve. So the following lemma is actually very important because it solves exactly that question. So two curves of genus 2 are isomorphic if and only if these Igusa arithmetic invariants satisfy the following property for some lambda non-zero number. So basically what we do is we notice we can define relation between tuples of invariants this way. So two tuples are related, equivalent, if and only if they are satisfied. There is a lambda sorry, that satisfies this property. So lambda to the power of lambda is the same as the degree of the corresponding coordinate. Okay, so this is an equivalence relation, and so the set of these equivalence classes is exactly correspond to each equivalent class correspond to the isomorphism class of a genus 2 curve, and the set of such equivalence classes is basically what it is, the weighted projective space, in this case with these weights 2, 4, 6, and 10, okay, over whatever field we are working with. So here are the main two questions now. Can we generalize this construction in general for higher genus? And can we actually now have some kind of way of counting points on these weighted projective spaces? And basically that's what this paper does. So again, I won't go over the projective, weighted projective space one more time. This is the definition. So you have the K star, I mean you have the field acting on this set of tuples on the affine space, and the equivalence class is the quotient of that action. You call it a weighted projective space. That is important here to define what we call the weighted greatest common divisor. So let's just say we have a point here over the rationals. We can actually easily make all the coordinates be integers because I can multiply by some constant and get rid of all the denominators. By the way, everything we are saying here over Q is true over any number field as we noted here, okay? But we're just, for simplicity, sticking to the rationals. Okay, so we are assuming this point has all integers. So the weighted greatest common divisor of this tuple of integers is the largest integer d such that raised to this qi, this weight qi, divides the corresponding xi. So if you actually make all the qi's to actually be ones, then of course this will be the normal GCD that we have for a tuple of integers. Okay, so we will call a tuple normalized when the weighted GCD is 1. And notice that for any point that we take here, we can divide by the weighted GCD or multiply by its reciprocal and get a tuple normalized. Okay, so now we know exactly what to store in terms of these tuples, right? We can find the minimal, some kind of minimal tuple that would be representative of a point in the weighted moduli space. Now what about the height? Okay, so let's just say we have a number field now, and everything is the same. I mean, the normal part of the math folklore in algebraic number theory, so the set of absolute values and the local degrees and the sum formula, the degree formula and the product formula. And the height now is defined as the product when the places move over the absolute values of the maximum of each coordinate to the power nv, nv is the degree of the completion, over qi, and qi was the weight. So notice this is really similar to the height in the projective space, but where all the qi's are equal to 1. And then in that case it actually is exactly the same. Surprisingly, everything works out. So this height defined this way does not depend on the choice of coordinates of p, so it's actually well defined. It is bigger or equal to 1. Okay, if we actually take this point, as we said before, normalize, so we divide by the weighted GCD of all the coordinates, then this is actually, for a large enough field, this is actually the same as the Archimedean height, so as h infinity, the point p, yes, and so it's actually very easy to actually compute it, and for finite extensions of the number field, the height over that finite extension is the height on the ground field to the power the degree of the extension. Also, this the following lemma is that the height is invariant under Galois conjugation, and this is true also for classical heights over projective spaces. And finally, our result is that the Northcote theorem holds for these heights as well, mainly that there are finitely many points in the weighted projective space with bounded heights. And that's basically what the paper does, and it proves some other additional properties of the heights and gives some open problems for the work. So thank you.